So we're going to go with Sig.Figs, significant figures, or significant digits. Significant figures or digits. Okay, now in math and in chemistry, you probably heard about the rounding, and the rounding is not really a mathematical thing. Rounding is a consequence of our laziness. We don't want to write a whole bunch of decimals, so we want to round this number. However, in physics, it has much more meaning, and significant means significant. It's important. So if we were to measure your height down to micrometer, this information would be insignificant, unimportant, because your height is changing throughout the day. It fluctuates. When you sleep, you will become a little taller in the morning. By the end of the day, it will become a little shorter, right? And even during the day, your height is changing. So measuring it down to even millimeter would be useless. So in physics and in general, like physical sciences, when you do measurements, you're limited by your instruments. This is, we talked about precision. So instruments tell you that you can measure down to a meter or millimeter or micrometer, but you cannot claim that you know the number with greater precision than the instrument allows. So we can write this down. So significant digits carry important and verifiable information. Acquired, can we use the word acquired? From measuring instruments. Measuring instruments. So measuring instruments could be crude, like a ruler in high school lab. They could be much more precise, like a micrometer. So let me actually write it down. So ruler, ruler. So ruler in school, right? So you can probably measure something down to a millimeter. So if you report something as a millimeter, like so many millimeters, that will be acceptable. But if you mention something like a fraction of a millimeter, probably that won't be acceptable because it's not verifiable. Anybody who measures the same thing over will get a completely different response, likely completely different response. And the precision would not allow them to see down to a fraction of a millimeter. The device called micrometer can obviously bring it down to about 0.1 micrometers. So this is, we're talking about 10 to the negative 7 meter. That's a reliable thing, meaning that you can replicate the same measurements with the same precision. Okay. Microscopes can be used as measuring tools. You should know that. So if you look at the slide and there's a scale there and you know magnification, you can figure out the size of your microscopic objects. So you can either have like a really small microscopic scale etched into the glass using lasers, and you can use it as, you know, to measure the size. Stopwatch. So it depends on what kind of stopwatch you have, obviously, right? The more expensive ones, mechanical expensive ones, may give you down to hundredths of a second. Obviously, electronic ones can give you much higher precision, right? So if it says 10 to the negative 2 seconds, then I can report my results as plus minus 0.5 10 to the negative 2 seconds. So this is what we'll call uncertainty. Uncertainty. So we're not certain if this is like within that margin, we're not certain about this number. Suppose I want to measure your height, right? And we use a meter stick for that. So this is the student, and we measure meter stick. So we don't see anything except 0, 1, and 2. So what should I report like on my scientific thesis, like the height of this particular student? What should be the number there? Go ahead, Cameron.
1.5, because you're supposed to read measure like one pass.
Yeah.
Estimate one pass.
Yes.
How much you can roll.
Right. So it'll be 1.5 meters, but I'm not certain about 1.5 because somebody says, well, maybe 1.6. Well, maybe 1.45. We're not certain about that, and our uncertainty has to be built into this measurement. So in a way, we're saying the height of the student is anywhere between 1 meter and 2 meters, which is true, right? We're not lying. Anywhere between 1 and 2 meters. But how precisely it is, we cannot tell because the instrument is rather crude. We cannot see that. If this was in centimeters, then you can actually see it at centimeters. And then, so your height will be then, let's say 1.65 plus minus point. Well, let me use centimeters. So this way I don't have to use decimals here. And it will be plus minus 0.5 centimeters. I can only see centimeter markings, but I can't see in between them like more precisely. So I can kind of guesstimate 0.5 centimeter halfway between 65 and 67, for example, right? And also like between 64 and 65. Let's say we used a much more precise meter stick. You see, precise means, it doesn't mean accurate, it means more numbers, more information. And we got down to a millimeter. So this will be millimeter. We can also claim that the uncertainty will be 0.5 millimeter, plus minus 0.5 millimeter. As you can see, the number of digits, where's my thingy? The number of digits is increasing, right? So here we have 2 significant digits, significant because they carry significant, reliable information. 3 significant figures, 4 significant figures. We can write down that information is equal to energy in a way. You can relate to this. To measure your height much more precisely, you will have to spend more time and more work and use more energy. Make sense? Really crude measurements take very little time. It's like making an estimate. Estimate takes less time than the actual physical computation, exact computation. Any questions about this? So Sig.Figs. So we have, I'm going to write down on this side. Usually we write them in the parentheses. So 1.5 meters has 2 Sig.Figs, right? 1.165 centimeters has 3 Sig.Figs, and 165.6 millimeters has 4 significant figures. Okay, so the more significant figures you can get, the more information you have about a particular quantity. Okay, now as I mentioned, in terms of your height, maybe millimeters would not be important. So you did all this job, you found your height exactly down to a millimeter, 0.5 millimeter, for nothing. Because a little bit later this will change and you can't report that as your height. So you have to also see like how the quantity changes over time and maybe over distance. So for example, gravitational acceleration. On your reference tables, you will see it's like 9.81 meter per second square. This is a general average of acceleration of free fall for the entire planet Earth. You will find that in many places it's like 9.79. In other places it's about 9.82. In some places 9.80. So the last digit is not significant. In fact, it should be written as 9.8. Well, let's put 0 here, or 1, since that's the 1, so 1, plus minus, and I would use some number here. I don't know what it is, because I didn't do like multiple measurements personally. I can't really claim that, but based on experience, and I've seen different numbers, probably this will be like 12. Okay, so this is my kind of, no, it's not, I'm sorry, go, too much. It will be, so 82.0, maybe like this. Okay, I'm gonna just guess. So we have 3 Sig.Figs, and the last significant figure, it has built-in uncertainty. So we can write this down as last digit is guesstimated. Estimate. Okay, makes sense? So we guesstimate because it is affected by uncertainty. So it could be more, it could be less. Okay, and last thing here is something you will have to probably look up and learn is when you add or subtract decimal, when you add the subtract Sig.Figs, right? You have to keep the least decimal. Keep the least decimal, right? And when you multiply or divide, you keep the least significant figures. Okay, let me go to this. I think we're like about to run out of time. I'll just show 2 examples and we're gonna wrap up. So if I'm adding 20.25 and then, hey, there you go. What's going on? If we're adding 20, what's going on? You guys see the white screen? Yeah. So for some reason it stopped working. So if we're adding 20.25, it's right there, okay. And then 10. So we do regular addition. And then we round to the least number of decimals, which will be 30. Which will be 30. So how do we understand this? Usually I give money examples. If you have $20.25 and somebody gave you $10, whatever. So you got 10 more dollars, but it was in form of like multiple bills or maybe even change or whatever. So somebody said, here, $10. And you don't know exactly if it was $10. You don't have information if this is exactly 10.00. Do you follow that? So let's say, I don't know, people are chipping in and then somebody says like, can you chip in as much as you can, whatever. So somebody's here, $10 in change. Even that person who gives the money may not know how much it is exactly, but it's about $10. So now what you're gonna do in your head is, okay, you have $20.25. You got about $10. So right now you should have about $30. Does it make sense? Because you have no information about the cents. It was lost here. Capiche? Yes, no, yes. Okay. And let's try multiplication. Multiplication. So if I multiply 2.1 times 5, right? So I do regular multiplication, which will be 10.5. And then I look which number has the least number of sig.Figs. Obviously 5 has one significant figure, 2.1 has two. So this has to be rounded to one significant figure. So this will be approximately 10. The 0 there is not significant because we didn't put the decimal point here. If I put decimal point, that would make that 0 significant. I can present this as 1, 10 to the 1. And this number is called mantissa. Mantissa. And if you can single out mantissa, you can always see how many sig.Figs you have there. In this case, mantissa has only one digit, so the number of sig.Figs is 1 in the answer. Questions about this? No questions. Okay, I'm gonna stop recording.